Hello, so this video is going to be about differentiating the function arctan of 1 over x. So I guess the first key point to note is that with this function, x is not defined for x equals to 0 because 1 divided by 0 is obviously going to give us an undefined result. So that's the first key point to make. And in fact, let's just consider the domain and range of this arctan of 1 over x function. So let's look at the domain and range of this function. And to help us do that, we can start by looking at the y equals arctan of x graph. So the arctan of x graph looks something like this. So it tends to pi over 2 as x tends to infinity. And it tends to negative pi over 2 as x tends to negative infinity, something like this. So we can clearly see that the range is between minus pi over 2 and pi over 2, and the domain is all real numbers. So x is defined for all real numbers. So that's our domain. And our range is, as we just said, so minus pi over 2 up to pi over 2 for the range. Okay, brilliant. So now we can use this information to help us out with the domain and range of the arctan of 1 over x function. So arctan of 1 over x. So that must have a domain which satisfies 1 over x being a real number. So the domain for this is 1 over x in the real numbers, just by swapping the variable 1 over x with the variable x up there, like that. So we know that must be true. So for 1 over x to be a real number, well, this is just exactly the same as saying that x is not equal to 0. So 1 divided by 0 is undefined, but 1 divided by any other real number is defined. So in order for 1 over x to be a real number, we just got to ensure that x is not equal to 0. So the domain is basically every real number apart from 0. So we can write it like this. So x in the real numbers apart from 0. Okay, so that's our domain. And then the range doesn't change. I mean, the range just remains the same because the arctan function has a range of minus pi over 2 up to pi over 2. So that just stays the same regardless of the variable that we put into the function. Okay, so that's the domain and range analysis done. So that can help us out, or it should help us out later later on in the video. So yeah, let's get on and differentiate this function then. So we're differentiating with respect to x, arctan of 1 over x. Again, we're differentiating a function of a function of x. This is going to be a case of using the chain rule again. And we've done this lots of times before. So using the chain rule in this case, this is differentiating the arctan of 1 over x function with respect to 1 over x. And then using the chain rule, we multiply this by the derivative of 1 over x with respect to just the variable x. And again, this is just by using the chain rule. So chain rule. Okay, so let me just make this writing a little bit smaller. Okay, yeah, so that's our chain rule, just using our chain rule formula. So now we want to differentiate this arctan function with a variable of 1 over x. So we've actually done this in a previous video. So we've already differentiated with respect to x the function arctan of x. And the result we got for this was as follows. So we got 1 over 1 plus x squared. So that was our result when we got this derivative. So what we can just do, because we're not differentiating the function of a variable of x with respect to x, we're differentiating a function of a variable of 1 over x with respect to 1 over x. We can just swap the variables. So this x there will become a 1 over x like that. This x inside there becomes a 1 over x like that. And so this x inside there has to become a 1 over x like so. And we can just simplify this fraction. So we get 1 over 1 plus 1 over x squared like that. And in fact, what we can do now, just to tidy this up a bit, is multiply the top and the bottom by x squared. So multiply the top by x squared and the bottom by x squared. And if we do that, we just get x squared over x squared plus 1 like that. Okay, great. So this first bit is x squared over x squared plus 1. And then multiply that by the derivative of 1 over x squared. So we've done this before. So this is the same as differentiating x to the power minus 1. Bring the power to the front, take away 1 from the power. You get negative x to the minus 2. But that's just the same as negative 1 over x squared. So we get negative 1 over x squared like that. And again, we can just do top times top, bottom times bottom. So we get negative x squared on the top, divided by x squared times by x squared plus 1. And what you'll notice is that we can cancel out the x squared there with the x squared there. And we're going to just get negative 1 over, so 1 plus x squared at the bottom like that. And so what we can conclude then is that when we differentiate the function arctan of 1 over x, we get the result negative 1 over 1 plus x squared. So that's the key result from this video today. But if you watch the last video, something you'll notice is that we differentiated the arccot of x function, and we got exactly the same result. So we got the result negative 1 over 1 plus x squared. So that's what we got from that video. So what can we conclude from this? Well, I mean, what we have to ask ourselves, or what we could ask ourselves, is this function the same as this function? So they've got the same derivative, but are they the same function? So let's just write this down here. So question, is it true that arctan of 1 over x equals to arccot of x? Okay, so to think about this then, let's draw the function arccot of x and look at the domain and range of that function. So the inverse cot function. So I mean, if we just think about what the cot function looks like, so we'll start with y equals cot of x. So y equals cos of x looks something like this. So this is the reciprocal tangent function. So we got the x-axis there, we got the y-axis there. So it kind of looks something like this. So I mean, well, I say the reciprocal tangent function, but really it's actually just defined to be cos of x over sine of x. I mean, this is the true definition of the cotangent function. So the cos function divided by the sine function. So yeah, what we can see then is as the x value tends to 0, we get a cot value tending to infinity, which would be true because cos at 0 is 1, sine at 0 is 0. So 1 divided by a tiny number is going to tend to infinity. So we get an asymptote there. We can see a point of intersection there, and that would be pi over 2. So cos of pi over 2 is 0, and sine of pi over 2 is 1. 0 divided by 1 is 0. So we get pi over 2 down there. And as x tends to pi, again, what you're going to get is that sine pi is 0. So a value divided by 0, we get an undefined value. So that's what the cot function looks like. So if we want to sketch the inverse of that, because that's what we're worried about here, we want to sketch the inverse y equals arccot function. So we just reflect this function in the line y equals x. And if we do that, let me do this in black ink again. So yeah, if we do that, then we should get something which looks like this. We're going to have an asymptote. So again, yeah, this is pi on the x-axis there. So the inverse function is going to have an asymptote at pi over there. and it's going to kind of look something like this. So we're going to have a point of intersection of pi over 2. It's going to be a negative gradient as well, because the original function has a negative gradient. And so it's going to look something like this. So it's going to tend to pi as x tends to negative infinity, and tend to 0 as x tends to infinity. So yeah, what can we see from here? So we can see that the domain is, well, x in the real numbers. So every value of x in the real numbers will give us an arc-cot value. And we can see the range. So the range of values is from 0 up to pi. So yeah, that's the arc-cot function. So let's think about the arctan of 1 over x function. So if we go back here, so we discovered that the domain of the arctan of 1 over x function is x in the real numbers apart from 0. So arctan of 1 over x is not defined at x equals 0. So let's make a point of this. So arctan of 1 over x is undefined. It's undefined at x equals 0. But if we think about this arc-cot function, so in fact, arc-cot of x is defined at x equals 0, and we can see by the graph that it's pi over 2. But arc-cot of x is defined at x equals 0. And in fact, arc-cot of 0, as we can see from the graph, arc-cot of 0 equals pi over 2. Okay, so we've got different domains for this function and this function. So they can't be the same function because they have a different domain. So therefore, what we can say from here is that they aren't the same function. So even though they've got the same derivative, because their domains aren't the same, they're not the same function. So yeah, let's just make a point of this then. So even though arctan of 1 over x does not equal the function arc-cot of x, because they don't have the same domain, so domains are different. It is still true, so it is still true that they have the same derivative. So it's still true that the derivative of arctan of 1 over x equals the derivative of arc-cot of x, and that derivative was -1 over 1 plus x squared. Sorry, let me write this a bit neater. So 1 plus x squared like that. And yeah, so I guess that's the key result from this video. So we've got two functions which have the same derivative, but they don't have the same domain. So even though they've got the same gradient function, they are not at the same function. So yeah, that's the conclusion from today.